In this video, we will talk about electrolysis, which is the use of electricity to drive a redox reaction. First, let's remember that electrolysis is a type of electrolytic cell. In an electrolytic cell, we convert electrical energy into chemical energy. This is the opposite of the other type of electrolytic cell, which was the voltaic cell, which we studied a couple of videos ago. In the voltaic cell, you produce electrical energy from chemical energy, and it's an exothermic reaction because it gives off electrical energy. In a voltaic cell, you have a positive cell potential and it occurs spontaneously. Conversely, in an electrolytic cell, you have a negative cell potential and it is non-spontaneous. Once again, to emphasize, the electrolytic cell uses electrical energy and it's endothermic. It requires some sort of power source from outside, such as either a battery or some sort of direct voltage, a power supply. And when we calculate the overall net potential of the cell, it is going to be negative. This negative voltage is the minimum, just the minimum required to force this non-spontaneous reaction to go. However, the cathode, where the site of the reduction, is now negative, whereas in a voltaic cell, the cathode was positive. As well, the anode in the electrolytic cell is positive. To start off, let's look at an example of where lead solid is placed into a solution of zinc ions and everything is connected with a wire. However, no evidence of reaction observed. The cathode does not change in size, the anode does not change in size, there are no bubbles. Because there are no reactions, we know this is a non-spontaneous reaction. If we look at our table of reduction cell potentials, the strongest oxidizing agent is zinc ions and the strongest reduction agent is lead ion. However, we notice that our strongest reducing agent is above our strongest oxidizing agent. Therefore, this is going to be a non-spontaneous reaction. If we look further for the reduction and oxidation cell potential in our reduction table values, we see that the reduction potential for zinc is negative 0.76 volts, whereas the oxidation potential for lead is positive 0.13 volts. If we're to add this together, we'll get a cell potential of negative 0.63 volts. Alternatively, we can use our shortcut method, where we take the reduction at the cathode minus the reduction at our anode. Again, these numbers are read directly off the table of standard cell reduction cell potentials. And here we get the same value of negative 0.063 volts. These negative values tell us that these reactions will be non-spontaneous, so lead will not be oxidized spontaneously in a solution of zinc ions. At first, these reactions would seem counterintuitive because we have to put energy into them. However, these reactions are good for the production of pure metals. For example, in the production of zinc, a lot of electricity is used in British Columbia to produce zinc and other base metals through the use of electrolysis. If we're to look at a diagram of an electrolytic cell, you would see two electrodes, one electrolyte, and a power source or a battery of some kind. And the power source is often the key giveaway as to whether a cell is a voltaic cell or an electrolytic cell. For an electrolytic cell, you must have a battery source or a power source. Often in diagrams, it's denoted as two lines that show as a battery source or a power source. As well, an electrolytic cell often occurs in one beaker, whereas a voltaic cell often have to be placed into two separate containers or two separate beakers separated by a salt bridge. The purpose of the battery or the power source is to act as an electron pump. It needs to drive the non-spontaneous reaction that is happening at the cathode. Therefore, electrical energy is converted into chemical potential energy inside the electrolytic cell. Let's compare the voltaic cell versus the electrolytic cell. Remember, these are both types of electrochemical cells. In a voltaic cell, the reaction is spontaneous because the overall cell potential is positive. On the other hand, electrolytic cells are non-spontaneous, they are endothermic reactions, and their cell potentials are negative. However, for both the voltaic cell and the electrolytic cell, reduction is happening at the cathode, but the positive electrode is the cathode, or the cathode is the positive electrode in the voltaic cell, whereas the cathode is the negative electrode in the electrolytic cell. Conversely, for the anode in a voltaic cell, that is a negative electrode, and for a electrolytic cell, the anode is positive. So those are the major differences between the voltaic cell and the electrolytic cell. However, the direction of electron movement is always from the anode to cathode for both the voltaic cell and the electrolytic cell, and the ions move towards the respective electrodes. Anions will move towards the anode, and cations will move towards the cathode. When we are asked to identify an electrolytic cell and the reactions that take place, it is equally important to identify the strongest oxidizing agent as well as the strongest reducing agent, keeping in mind that water is often present in aqueous solutions. Then determine the strongest reduction reaction that's going to happen at the cathode, and then the oxidation reaction that's going to happen at the anode. Then balance the half reactions to balance the number of electrons transferred. That determine the overall cell potential by using this equation. Again, it is the reduction potential at the cathode minus the reduction potential of the anode. For electrolytic cell, the overall cell potential will be negative. This is also what is called a minimum voltage for this electrolytic cell to occur. Remember, this is the minimum voltage, and when in lab practical situations, this voltage will often need to be higher than the minimum required. Lastly, draw the diagram if it's requested. Let's look at the electrolysis of lead nitrate. Identifying the strongest oxidizing agent, we find that lead ions is our strongest oxidizing agent, whereas water is our strongest reducing agent. At our cathode, let's write the reduction reaction of lead ions into solid lead, and we see that the cell potential there is negative 0.13 volts. At the anode, we write the oxidation equation for water, and the cell potential there is positive 1.23 volts. Because the reduction of lead requires 2 electrons, whereas the oxidation of water provides 4 electrons, we need to double the number of reduction reactions by 2, and then overall our net equation reads as such. And then if we to add the cell potential, we would see that it's negative 1.36 volts. That means our battery's power supply must have a minimum voltage of positive 1.36 volts. For our diagram, we have one beaker, and this beaker is filled with lead nitrate. For cathode, we have a lead electrode. The reduction of lead ions into solid lead will slowly increase the mass of our cathode over time. For our anode, where the oxidation of water is happening, we can use an inert electrode such as carbon, or we can also use something like platinum or palladium. The flow of electron will always be from the anode to the cathode. However, we also require a power supply set to a minimum voltage of 1.36 volt to drive this electrolytic endothermic reaction. As well as water is oxidized into oxygen gas and hydrogen ions, we produce a lot of hydrogen ions over time. Therefore, as this solution is allowed to run, the concentration of hydrogen ions, it will rise and the pH will drop. And lastly, we notice that the positive terminal of our battery source is connected to our anode, positive, and the negative terminal of our battery source is connected to our cathode, which in this case is negative. One example of an electrolytic cell is what's called a secondary cell. In this case, we're going to look at a nickel-cadmium cell, and this is one of the first form of a rechargeable battery. During normal operation, the cell discharges and it functions as a voltaic cell and produces electrical energy from chemical energy. However, when this battery is plugged into an electrical outlet, it is then recharged. The electrical energy forces the electrolytic reactions so that electrical energy is stored as chemical energy. It is during the recharging of this secondary cell that this cell is considered to be an electrolytic cell. Nowadays, nickel-cadmium cells are not as prevalent as other cells such as metal hydride or lithium rechargeable batteries. Another application of electrolysis is the production of elements such as zinc and copper. Now, most of these compounds are usually found in nature as oxides with oxygen. However, we can use electrolysis to provide pure metal compounds. However, there's two problems if we were to use an aqueous solution. Most of these metals are not very soluble in water, and water is a relatively strong oxidizing agent and will be reduced preferentially over our metal ions. Therefore, we have to use a system that does not involve water, and one way to do it is to use molten or melted ionic compounds. The molten compound not only serves as the reactant in the reaction, but it also serves as the electrolyte where the ions can conduct. For example, strontium was one of the metals that was first purified using electrolysis of the molten compound. Here, you'll notice that the strontium ion is present in the liquid form and not the aqueous form, as well the chloride ion is present in the liquid form. There is no water in this molten reaction. Similarly to other reactions, we have the reduction at the cathode, and this is the reduction of strontium ions into strontium solid, and oxidation at the anode, where the chloride ions are oxidized into chlorine gas and producing 2 electrons. Both of these reactions involve 2 electrons, so they're balanced. All we have to do is add them together. So the overall reaction is the reaction of strontium ions with chloride ions to produce strontium solid and chlorine gas. In this example of strontium chloride, this would not have been possible in an aqueous solution because water is a much stronger oxidizing agent than strontium. It will be reduced to hydrogen ions and oxygen gas before the reduction of strontium ions into solid strontium. Similar to our previous electrolytic cells, the cations are moved towards the cathode. However, it is then reduced to the metal at the cathode, whereas the non-metal anions are moved to the anode and then oxidized to a non-metal, either as a gas or as a liquid compound such as iodine. One last application of electrolysis is in the form of electrorefining. Here, industrial processes convert relatively low purity copper into high purity copper. High purity copper is required in metal wires because it improves their conductivity. The impurities such as gold, silver, platinum, and iron are recovered at the anode and can be then sold to lower the overall cost of the process. In the electrorefining of copper, we connect a slab of relatively impure copper at the anode. Here, all the metals are oxidized, including the copper, zinc, iron, gold, and silver. At the cathode, we have a very thin sheet of pure copper. As the oxidation of copper ions from the anode into the solution occurs, we have additional reduction of copper ions from the solution into the very pure cathode. Any of the remaining impurities, the silver, the gold, the platinum, the zinc, or the iron, will fall down towards the bottom of the container and will not be reduced at the cathode onto our pure sample of copper. This process produces a copper sample that is about 99.98% pure and is suitable for use in electrical wires. Another application of electrolysis is called electroplating. This is when a thin layer of expensive and relatively unreactive metal, such as silver, gold, zinc, or chromium, is plated onto another object. Now, a product made from precious metals such as gold and silver are very brittle and soft, but we can use them to improve the conductivity of other objects. So we could also have things like chrome bumpers or spoons and utensils coated with precious metals such as silver and chromium to make them look better and to resist corrosion.